we measured a 400-year-old landslide. And you're probably wondering why. Well, it all started after I graduated from my PhD and moved to Switzerland to do a postdoc with Georg Hetteny. When I arrived, we were brainstorming projects I can do while here, and the topic of the ovi came up. And the ovi is the local name for the landslide event and the deposits left behind over 400 years ago in the region of Corbeil and Yvonne, near the eastern end of Lake Geneva. On the 11th of March 1584, a 5.9 magnitude earthquake triggered a landslide at the top of the mountain. Then, after some days of heavy rain, on the 14th of March 1584, an aftershock of magnitude 5.4 brought all that material down the mountain, partly covering the villages of Corbeil and Yvonne. So, there was some concern in the community that something like this could happen again if another earthquake occurs. And while this area has been mapped at the surface level, not much is known about what's happening below, like how thick the ovi deposits really are. So we set out to answer these questions using geophysics, and this is where a PhD in geophysics comes in handy. Here I am, struggling with the plugs of one of the seismometers we used to measure ambient seismic vibrations. And ambient seismic vibrations are vibrations from everyday sources, for example, from humans, oceans, wind, etc. So basically not from special events like earthquakes. We can use these ambient recordings to know the frequencies at which there can be local amplification of ground motion if there is an earthquake. These recordings can also tell us about the depth of the boundary interfaces, for example, between sediment and rock layers. So it can tell us about the thicknesses of these layers. The method we use to find this out is called the horizontal to vertical ratio, and it's exactly as the name says. It's the ratio of the horizontal to vertical components of the signal. We did a total of 54 measurements, with 45 measurements within the trace of the ovi and 9 measurements outside. In the upper part of the ovi, which is called Plan Falcon and is the source area of the landslide, we observed mostly lower frequency peaks, which could suggest a deeper boundary interface and thicker sediment layer, compared to downslope, which had higher frequency peaks, suggesting a thinning of the layer downslope. And using these results not as a direct measure, but as an indicator of areas where the ovi deposits are more susceptible to remobilization, so moving downslope again if there is an earthquake, we found that Plan Falcon and the slope of loose material just below were the most vulnerable areas. We did 2 other techniques in this upper part of the ovi: electrical resistivity tomography, or ERT for short, and ground penetrating radar, or GPR. We did 1 ERT line in purple and 4 GPR lines in green. These 2 techniques give us images of the subsurface by using electric current in the case of ERT and electromagnetic pulses in the case of GPR, and injecting them into the ground. The ERT showed a less resistive layer in blue, which corresponds to a weak signal in the GPR, and we interpret this layer as surface runoff deposits. This layer is underlaid by a more resistive layer in yellow, which we interpret as the ovi deposits, and it reaches a depth greater than what we could image. We were able to use these results and topographic profiles to estimate the thickness of the ovi deposits in this area, and we came up with an estimate of 50 to 100 meters thick. We also did 1 ERT line and 3 GPR lines in the middle of the ovi. And here we see the more resistive layer in yellow has a thickness between 3.5 to 4 meters, which seems to correspond to a stronger GPR signal. So the ERT and GPR results show a thinning of the sediment layer downslope, which the horizontal to vertical ratio also suggested. So in order to see what we were actually dealing with, and to have a physical sample to compare with the geophysical measurements, we drilled a core in the middle of the ovi. We drilled here because it was easier to access than Plan Falcon, and because we could also drill a not so deep core and see the entire ovi layer. The core was 10.6 meters deep, and the good news is it confirmed the results of the geophysics. So the core showed that the ovi deposits were about 3.5 meters thick with angular clasts of gravel and cobbles in a clay matrix, and there was a water-saturated zone at the boundary of this layer, which is most likely the water table. So in the end, we saw that the thickest deposits were in the upper part of the ovi, possibly reaching as thick as 100 meters, and these deposits thin as you move down slope. We also determined that if an earthquake occurred, the most susceptible regions where these ovi deposits could move again are in Plan Falcon and the slope just below. But the probability of a large magnitude earthquake in this region is relatively low, and the fact that there is a lot of forest cover and only a few houses reduces the risk. So, we were able to measure a 400-year-old landslide. Sometimes the weather was not so great, sometimes it was perfect, but we still made it through either way, and it's always worth it in the end, especially when you could witness things like these.